Hi, my name is Lin Sui. I'm a master student of Lambda Group of Nanjing University. Today, I'm pleased to present our work entitled A Simple and Efficient Pipeline to Build an End-to-End Spatial-Temporal Action Detector. Recent years, remarkable successes are made in the spatial-temporal action detection field. Former works usually selected to build two-stage detectors. They extract the center frame called keyframe and feed it into an offline person detector to generate person proposals. FPN with ResNext 101 pre-trained on MS COCO is the most common choice for the offline person detector. Once proposals are obtained, the detector performs multi-label classification based on them and produces the final results. As for the spatial-temporal action detection benchmark, AVA, which is a sparse annotated large-scale dataset, is the most popular choice recently. Videos are annotated only 1 frame per second in order to relieve the cost of annotations. However, there are several problems in former works. Firstly, the offline person detector is time-consuming but essential. We could find that the offline person detector occupies over 80% of computation. Hence, the heavy offline person detector impedes real-world applications of spatial-temporal action detection. Some former works tried to build end-to-end detectors, however, they could not get satisfying performance. As shown in the table, former end-to-end detectors resort to the help of classification head with attention mechanism to remedy the accuracy loss caused by removing the heavy offline person detection. Secondly, the sparse annotated large-scale dataset is not fully utilized. Former methods only use the annotated keyframes and ignore unlabeled frames that accounted for the majority. Our proposed SE-STAD pipeline is shown here. SE-STAD consists of 2 main parts. The first part is a simple but effective end-to-end spatial-temporal action detector. Besides, the second part is temporal label assignment algorithm used to generate high-quality pseudo-labels during the semi-supervised process. When building the end-to-end one-stage detector, unlike previous methods which focused on classification head to remedy the loss of accuracy, we emphasize on the localization part and the training policy. We find that anchor-free heads and generating dense output proposals are 2 essential factors to build a simple but effective one-stage detector. In our SE-STAD, we build a feature pyramid architecture. Channels according to the keyframes are fed into the anchor-free FCOS head to generate person proposals. Person proposals are not processed with NMS before feeding to the classification head. Finally, we use the simplest classification head to generate the final detection results. As we known, AVA dataset is accompanied by multi-label and long-tail classification problems. Hence, widely used pseudo-label generating methods generate low-quality pseudo-labels. To utilize the unlabeled part, SE-STAD proposed the temporal label assignment algorithm. TLA utilizes the temporal constraints of spatio-temporal data and treats pseudo-label generating as label assignment process based on adjacent keyframes and predicted person proposals of the medial unlabeled frame. Assignment result is obtained by minimizing the cost. We perform experiments on 2 widely used STAD benchmarks and SE-STAD achieves excellent results. On AVA, our SE-STAD can achieve around 2 map boost and around 80% flops reduction steadily. Compared with former end-to-end detector, SE-STAD can also achieve better accuracy and computation accuracy trade-off without the help of attention classification head. Tables in the right part demonstrate that localization head and training strategy parts are essential. Besides, compared to other methods, TLA can bring more accuracy gain. SE-STAD also have great generalization ability. SE-STAD can cooperate with other backbone and stronger action classification head. Cooperating with a simple attention head, the ACRN head, SE-STAD can obtain additional gains. One of the most important advantage of SE-STAD is the low computation cost. Using the same slow-fast R50 backbone, SE-STAD reduced the proportion of computation of the localization head from 81% to 12%. As shown in the table, SE-STAD can achieve better accuracy with much lower computation cost. Thanks for your listening.